Let's do a brief catch-up from the previous lecture where we looked at elastostatics in higher dimension. And essentially what we did is the same thing we did over and over in this course, right? We defined our domain, and well, we said that there are three types of boundary conditions. So we define our parts of the domain as the part where you are prescribing the displacement, gamma u, the parts where you are prescribing your Robin boundary condition, gamma h, and then pretty much the rest is gamma t. So if you have a zero traction, that is also part of gamma t. You prescribe Newman boundary condition. And then, well, given some quantities, body force, prescribed displacement, prescribed traction, and the elastic support for the Robin boundary condition, we stated the problem in strong form, right? We say, well, the divergence of the stress tensor plus the body force has to be equal to 0, and that is at every point inside your domain. And we said that is not alone to define the boundary value problem. We need, of course, boundary conditions, and so we have Dirichlet boundary condition, Newman boundary condition, and a Robin boundary condition. And with that, we define the boundary value problem so that it is well posed. Now, we said we never do this, we never solve this problem, especially elasticity in higher dimensions. Even for the slightest, more complex configurations that deviates from a circular domain or a square domain, then the chances that you get the exact solution are almost nil. And so we say, well, we're going to define a weak form equivalent version of a problem. Remember that these are equivalent because we're still living in infinite dimensional space. And we said we're going to take our differential equation, weight it with a test function, and set the integral of that equal to 0 for all test functions in some space. And we define that space as it's a vector valued function space. So vector value means now we have a vector that every component of that vector has is defined in a space, and of course that space is the Sobolev space. So we're looking at functions again that produce finite strain energy. And you remember the idea was, okay, we're going to use functions that do not blow up inside the domain that would otherwise cause infinite strain energy. And we also make sure that those functions vanish in the Dirichlet part of the boundary, and by doing so, we basically get rid of the reaction force that arises when we do the divergence theorem. So we use an identity, right? And we use that identity, we plug it back into the formulation, and so we get this expression here, where now, instead of having the divergence of the stress tensor, which would require a second order derivative in the displacement, now we kind of balance those derivatives, right? Because now this term here requires just a single derivative on the displacement and a single derivative on the test functions. And then, well, we looked at this particular term here because we can apply the divergence theorem on that term, and this is what we do here, right? We apply the divergence theorem, and so basically we transform an integral over the domain to an integral over the boundary. And so remember that the boundary is, of course, decomposed in three parts. You have the reaction force that we nicely get rid of by just satisfying the fact that the test functions are equal to 0 in that part of the boundary. And then you have the Newman boundary condition and your Robin boundary condition. And so the final version of your weak formulation is stated here. This whole expression here on the left, you have the bilinear form. Again, bilinear because it's a function of both u and w. And then on the right-hand side, the linear form that is only a function of w. And obviously, if you don't have Robin boundary condition, this term would go away and that term would go away, right? Making the problem simpler. And that is normally the case. Normally, we don't actually apply too many Robin boundary conditions, but we are mostly working with Dirichlet and Newman boundary conditions. Okay, we stated the problem in weak form, and again, keep in mind that still this is in an infinite dimensional space. So now the Galerkin projection would basically adopt finite element spaces that are living in a subset of this space here, and then only then you can actually solve the problem, right? And we also talked a little bit about how to deal with non-homogeneous essential boundary conditions, and essentially it's very straightforward, right? We basically apply a trick. We say, well, I'm going to write the solution as the sum of two components. one component that satisfies a priori the Dirichlet boundary condition, and another component that I don't know, so that is the unknown, but I take from the same space as the test function. And if I do so, again, we are in the Bubnov-Galerkin approximation, and now I get the nice properties of the Bubnov-Galerkin approach, which is basically my stiffness matrix is symmetric and these sort of things, okay? So that is the way we deal very straightforwardly with non-zero essential boundary conditions. Okay, so now we are ready to move on to another method, right? So we said in the beginning of this course, we're going to look at two methods. One is the H version of the finite element method, where we improve the approximation, right? Remember, the finite element method gives you an approximation to the solution, right? Unless, of course, you are lucky enough that just approximation, that the approximation happens to be the exact solution, but that is for very simple problems. In the H version of p-FEM, we basically have, we reduce the error in the approximation by simply making the elements smaller. And it makes a lot of sense. We know that very highly nonlinear functions can be better and better approximated as long as we make our elements smaller and smaller. So that was the basis of the H-FEM, and this is what we have been doing so far. Now we're going to keep our mesh fixed, and we're going to reduce the error by increasing the polynomial interpolation order, okay? And that is the basis of what is called the P version of p-FEM, and that is what we're going to study today, okay? So we start with, let me just remove this. Okay. All right. And I'm going to borrow some images from the book, and I'm going to take this guy and I'm going to paste it here. So let me draw your attention to something. If you look at the plots, at the plot on the left, right, the figure on the left, you see the monomials, and the monomials with increasing degree of polynomial interpolation order, right? So this is the linear one. Then you have the quadratic, then the cubic, the quartic, and so forth. So what do you see? As we increase the polynomial interpolation order, what do you see?
They go to one approach more faster.
The approach?
The endpoints faster.
No. What can you see? As we increase the polynomial order, yeah?
They develop some sort of a valley. So what you see is that especially for lower values of C,
Yeah.
the output is very close to 1. So I imagine that there is very small differences between.
That's not what I'm looking for, though. So what you see here, of course, for the even functions, so obviously you have odd and even functions, and for those you see the remarkable difference on the left. But as we increase the polynomial interpolation order, what we see is actually these functions start to look very much alike, closer and closer. So at some point, as we increase the polynomial interpolation order, you're going to add a new function that looks pretty much the same as the previous function that you added. So that is not very good for the interpolation properties of a polynomial. And in fact, this will lead to ill conditioning, right? So your stiffness matrix will become more and more ill conditioned, right? That's what's happening. So if you add a new function and that function can more or less be already represented by the basis that you have, right? Adding it is not going to help much. And in fact, it's going to make things worse because it's going to make the problem more ill conditioned. That is the reason why we use these type of polynomials. And you can see those polynomials are remarkably different. They are orthogonal. Orthogonal means that if I take these two polynomials and I multiply them and I do the integral in the domain -1, 1, their product is equal to 0. Yeah?
Is the left Lagrangian?
Sorry?
Is the left figure, is it Lagrangian?
This is just monomials. You see, it's just represented like this. And these are called Legendre polynomials. And of course, it's one kind of orthogonal polynomials. There are many kinds of orthogonal polynomials. You also have Chebyshev, for instance. But these are the polynomials that we're going to use to construct our basis, simply because we know that if I'm going to add a new order, I'm going to increase the order of a polynomial, I know that I'm going to really be introducing something new, right? That is not something that can be already represented. So we're going to define our space of polynomials, SPH, as the functions u such that u belongs to the energy space. This has not changed. We are still going to be dealing with functions that are going to produce finite strain energy. But now u of x is going to be a polynomial. So it belongs to a space P, Pi of EI. That's an element for all x that belongs to that element. Obviously, I in the range 1 number of elements. Where PPI is basically the space of polynomials of degree less than or equal to Pi. Obviously, we're talking about complete polynomials, right? It doesn't make sense that I have a cubic polynomial and I'm not really considering the quadratic components, right? So we're talking about complete polynomials. Okay, so let's see how these polynomials look like. So we're going to use the Legendre polynomials, which are the ones that I show here. These are the Legendre polynomials. As the basis. And well, our polynomials, our shape functions are going to look something like this. So for p equals 1, so these ones basically don't change, right? These are going to be the same. Phi1, Phi2 is equal to 1 plus c divided by 2. Notice that I use c, so that means that I'm defining already these polynomials in the master element. These don't change. And so for p equals 2, I'm going to be adding something on top of that. And that is a cool thing. Like, I'm going to be improving my basis hierarchically. So I'm going to keep the standard p-FEM linear shape functions. And then if I want a quadratic interpolation, well, I'm going to add a quadratic function on top of that. I'm not going to touch my linear interpolation. And that basically means that I'm improving or enhancing my basis functions by simply adding new information, right? And so for p equals 2, of course, I'm going to keep these ones. But then I'm going to be adding something else. Let's say that one, right? And this is going to be phi3, which is equal to phi hat 2, and you will see what that means in a second. Well, and then for p equals 3, this is the same, this is the same. Of course, I'm going to keep this one. And then I'm going to add one more. And that one more is going to look something like this. And this is phi4 is equal to phi3 hat. Okay, so let's see, what is this phi hat function? Well, it's a helper function that is going to be defined as the square root of 2j minus 1 divided by 2. and then the integral between -1 and psi of L j is -1 of t dt, which is equal to, I don't know by heart these functions. Once you code them, you forget about them. So 2j minus 1. And then you have the Lagrangian polynomials popping up here like this. Lj minus 2 of c. And then, of course, j2 all the way to order p. And what you see in this function, this is a helper function, right? That is basically helping me to construct these polynomials. So my third check function is going to be phi hat 2. So then when j is equal to 2, I plug that here. And then if you notice, I use basically L2 and then L0. And those are Legendre polynomials. And those Legendre polynomials are pretty much well defined. And something interesting about this is that the more you increase your polynomial order, you are going to be reusing stuff that you used for lower orders, right? And so you can gain a lot of computation by doing this, right? So say you want a polynomial interpolation order 10, well, most likely you are going to be reusing all these Lj from 0, 1, 2, 3 to construct your entire polynomial order 10. Yeah?
When you say you're improving the polynomials or improving the functions,
Yeah.
you compare it to doing a Taylor expansion, for instance, and instead of neglecting the higher order terms which you would do in linear functions, instead you would improve it with a higher order term by increasing with another Legendre polynomial.
Yeah, so of course you're adding more information to your basis, right? It's not the same thing as a Taylor expansion, that just keeping more. That is basically used to approximate the derivative. So the more terms you take, the better the approximation. But this is different. So here we have a basis of functions. We use that basis to compute our approximation, and it makes sense that if we're going to use a higher order basis, the approximation should be better, right? Unless somehow, I don't know, there are cases where you add a polynomial degree of this order and that didn't really help much. Maybe because you already got the exact solution with the previous order, that happens. And so the Galerkin projection is going to assign 0 coefficients to the new polynomial order. But in general, you would expect that if you don't capture the exact solution, adding more polynomial functions to your basis would obviously improve the approximation, okay? So these functions that I wrote here, right, have a really nice property. And the property is that if I take 2 of these functions and I do the integral in the domain of integration, right, -1, 1, and I take their derivatives, this is equal to delta ij, which is our Kronecker delta. So basically, if you take 2 of those functions, that integral of the derivatives is equal to 1. If those functions are different, is equal to 0. And you may argue, well, why do you take the derivatives? Someone?
Sensitivity analysis?
Sorry?
Sensitivity analysis?
No. Why you take the derivatives and not just the functions themselves? Why do I want the derivatives to satisfy this property? Yeah?
Because you take the derivative of your shape so well.
Yes, that is the reason. Thank you so much. Yeah, so when we're building our stiffness matrix, of course, we need the first order derivatives. And so since the objective is to make the system the best possible conditioned system, right, by making sure that the derivatives of those functions are themselves orthogonal, right, we improve the condition number the most. And that is why we're taking the derivatives. Okay?
No. Can you repeat that, please?
Okay, well, I'm writing it here. This is done because in our bilinear form, we need the derivatives of the shape functions. To be orthogonal. So basically, the derivatives of these functions are the Legendre polynomials that are orthogonal. Okay? That is how this function is defined. So these functions are defined so that their derivatives are the Legendre polynomials. Okay. So obviously we talked a little bit about this, and one main advantage is that we get the best condition number and actually in the project you're going to look into this. If you recall, in the first exercise at some point I asked you to compute the condition number of both h-FEM and p-FEM and see how that behaves, and you will find something remarkable. And the other thing that we discussed is that, let's say for instance, if we go from quadratic to cubic, we can reuse previous computations. And that is, of course, because of the recursive nature in which we compute our polynomials. Remember that we have this expression, we're using Legendre polynomials. So if you have a higher order polynomial, well, you would expect to reuse some of that information. So a naive implementation would actually compute these polynomials from scratch, but if you do it a little bit smarter, then you can cache some of your results and just simply get them back, right, and reuse them, right? Notice also that this is basically, it can be done in a recursive manner, and if you see the book, actually, that is what we have done in the book, right? We have a very little piece of pseudocode where when we can compute these shape functions in a hierarchical manner. And Martin, tomorrow afternoon, is going to work a little bit on this with you so that you understand a little bit how these polynomials are computed. And I think that right now, let me see. Yeah, I'm gonna copy this guy here, actually, so that you have also in your notes the complete picture. Yeah, so now you see that my quadratic polynomial is actually facing down. Okay, so how do we use this? Now that we have the basis that we're going to use, we just simply need to write our approximation, right? Where you notice that nothing really has changed. In fact, it is exactly the same approximation that we use for standard FEM, just that now, depending on the order of the approximation, we're going to have many, many, many more terms. Now, I want you also to pay attention to something that is going to, I mean, we're going to discuss this a little bit more later, but notice that my linear functions, as we said, are the same as those of h-FEM, but every other function that is higher order basically vanishes at those points. They are exactly zero. In 1D, they are exactly zero at the endpoints of the element. And this is very interesting for a few reasons that we will discuss later. Now, also notice that there is no more partition of unity anymore, right? If I look at the elements and I sum up all the functions at any given point, right? I know already that the sum of these two add up to 1. So those two satisfy the partition of unity. But the moment I add a quadratic function, that's it. No more partition of unity satisfying the element. So we lose that ability. Is that important? Well, it is. If you want to know what is the value of the displacement field or the temperature field inside the element, there is no other way but to evaluate the whole polynomial. You have no other chance. You have to do it, okay? But because these guys are exactly 0 at the end nodes, well, if you want to obtain the temperature of the displacement field at the ends of the element, you can still relate those to the degrees of freedom that you obtain, okay? Just so that we know. Okay, well, but this is for the field. What happens with our geometry? So we know already that in p-FEM we use with what kind of approximation? Subparametric, isoparametric, or superparametric? Isoparametric. So what do you think is going to happen here? Huh?
You will need a subparameter.
Subparametric. Now, our geometry, well, in 1D, it doesn't make sense to represent my geometry with a 6th-order polynomial, does it? And so we're going to keep that. Sorry? First order, linear, right? The same. And so my x as a function of c is equal to 1 minus c divided by 2 xi, that is the left node, and so now the Jacobian remains exactly the same as in p-FEM. Okay? Okay, well, we're going to look at an example just so that you know how this is actually going to be implemented in the actual code. So there is a little trick in the implementation of p-FEM. This is something that you will have to do for the project to solve exercise number 1, right? But keep this tip in mind, okay? This is it. This is the key here. Everybody with me? Yeah? If you are smart in the way you build your connectivity table, the connectivity table, right? Implementing p-FEM takes no effort whatsoever. Keep this tip in mind. Keep it in mind. Remember, now we no longer have nodes. And I will explain a little bit what that means. But if we think about these higher order coefficients as nodes, and we build our connectivity table in terms of nodes, implementing p-FEM is very, very easy. Okay, so keep this in mind. Let's make an example so that you understand a bit how this is going to work in the code. So say we have a one-dimensional problem that looks like this. And somehow I want, well, p equals 1 here, p equals 2 here, p equals 3 there. Okay? Well, let's see what are the functions that are acting. So if I remember, well, we had our linear functions. Let's make it like this. Our linear functions. Obviously, this one is phi1, phi2, phi3, phi4. Then I'm going to have this one here and this one are going to both have my quadratic function. So I have something that looks like that. phi5, phi6, and then finally in the last one I'm going to have something that looks like this, and that is going to be phi7. So
these are 3 elements, or is it
these are 3 elements.
3 elements?
In one element you have p1, in the second p2, in the third one p3. So these were the linear, right? Okay, and now we're going to write our approximation. So our approximation, obviously, is the sum of phi I ui, right? And so we have phi1 of x u1, that is the first linear function, plus phi2 u2, plus all the way phi7 u7, which is obviously the same way we write right? I normally also like to see this approximation as written this way. Iota h plus and I like to write it this way because this function here, the first part, is basically my iota h is my linear h-FEM approximation, right? So obviously, if you look at this problem, right, phi1, phi2, phi3, and phi4 are going to be composed here in that part, right? So this is my linear term. So this is my linear h-FEM. Well, and all here is my nonlinear terms. And I like to write it like this because you can already think about p-FEM as some sort of enrichment, right? We are enriching the linear finite element space with nonlinear polynomials. And as you know, this course is actually a prerequisite, or it was a prerequisite for the enriched FEM course. And so I like to think about linear polynomials as nonlinear polynomials as the first step towards thinking in terms of how you enrich a finite element space to improve the approximation, okay? Okay, well, let's see. If I have to compute the field, the displacement, or the temperature at this location, at node 2, right? Well, notice that there is only one shake function that is non-zero at that location. Because as we said, all the nonlinear functions are basically going to vanish at the locations of the nodes. So at that location, I have UH of x2 is equal to phi2 evaluated at x2, u2, but I know that this whole thing is equal to 1, and so is equal to u2. So in that regard, at the locations of the nodes, nothing really changed with regards to the h-FEM version of FEM, each version of FEM, right? Like the location, at the location of the nodes, the degree of freedom represents the actual field. And that is because, again, here, the linear shake functions are still satisfying this Kronecker delta property. Remember the Kronecker delta property? What it was saying, right? Either 1 or 0. But that's only happening for the linear functions. So as long as we are in the nodes in p-FEM, nothing has really changed. We're still associating the degrees of freedom, the linear degrees of freedom, to the actual field, okay? Okay, so the DOF has the same meaning. say physical meaning, right? As h-FEM. Okay, well, what happens at the middle? Say at the middle of E3, which is our cubic element, right? Well, we can compute UH at x3 plus x4 divided by 2. That is going to be equal to my linear function phi3. Well, let's say, just to help me, this guy is, I call it x prime. So it's phi3 evaluated at x prime, u3 plus phi4. Those are the linear functions evaluated at x prime, u4 plus phi6 at x prime, u6. Well, since I'm exactly at the middle of the element, well, it turns out that my phi7 is equal to 0, right? So then I don't evaluate that, right? And, well, because I'm exactly at the middle, phi3 and phi4, those are equal to 1/2. So this one here is 1/2. This one here is 1/2, right? And so now you can understand that the degree of freedom U6 is no longer the field at that location, right? And in fact, you can think of these generalized degrees of freedom. These are by the way, these are called generalized degrees of freedom. You can think of them as more related to the high order derivatives of the function, right? So if you want to evaluate the field inside an element, you have no choice but to evaluate the complete expression. That is what we said earlier. So U6 has no longer the physical meaning. Of the primal field variable. Okay? Well, if I take the second derivative of UH, then I get U6, because of course everything else drops. Second order derivative of phi6 of x with respect to x2. Now, of course, keep in mind that I'm evaluating these at x prime. That's why there is no phi7 either. And so U6 is more related to higher order derivatives. Okay? All right. Now, of course, yeah?
What is U6 here? Because when you look at the element,
Yeah?
it's very logical to say, well, okay, but U1, U2, U3, U4
Yeah.
For every node there, but where does U6 come in? Is it also a node, a physical node in between? Or
Yeah, so, and this is the discussion that I wanted to have towards the end of the lecture, but let's move it to this point in the lecture. Okay, so in h-FEM, when you think of a node, right,
Yes.
you normally say, well, there is a shake function that is associated to that node, right?
Yes.
And so you associate, of course, that function that is equal to 1 at the node, when in fact, that function should not be associated with a node in space, with a point in space. It should be associated with the region on which the function is non-zero. But we still have this in our minds, right, because we come from this h-FEM world, that a function is associated to a location in space, to a node in space. Well, now that's no longer the case, right? Now, if you look, for instance, say I look at this phi5, right? It's a quadratic function. So which node are you going to associate to that function? Well, obviously, you would say, well, let's take the middle node, right? Because then that is the highest value of the function, right? And so if we continue logically from our h-FEM mindset, you would associate the middle node with that quadratic function, right? All right, now let's take a look at phi7. So now we have a function that basically is the same here and here. So then which node do you associate? The one on the left or on the right? Okay, let's make a rule. Let's say the first point at which the function becomes the max. But then you're going to have high order polynomials, right? And so, in essence, we have to move away, when we deal with p-FEM, we have to move away from this mindset that now a function is associated with a location in space. And you have to think about these generalized nodes, generalized coordinates, as a node that basically can happen anywhere in the bar. Any point along the bar is a point I can associate that function. In fact, we should associate those degrees of freedom to functions that are non-zero in a range, right? That is non-zero. And that is a little bit the mindset that we have to change. But still, if, again, going back to the tip that I gave you a few minutes ago, if you think about this p-FEM in terms of implementation as generalized nodes and you modify smartly your connectivity table, then implementing p-FEM becomes very, very straightforward.
Because at your nodes there is actually something there, right? So
Yeah.
Okay. And this then a big difference with, for example, Lagrangian like the Lagrangian elements, right? Because
Yeah.
you actually add nodes in between.
Yeah, well, for the Lagrangian shake functions, we can still go back to this mindset of basically having a node associated with a function, right?
Yeah.
So for instance, if you take the quadratic Lagrangian element, right, you have three functions. The first one is equal to 1 in the first node and 0 at the other nodes.
Yes.
The second shape function is equal to 1 in the middle of the element, that the quadratic, so the three functions are quadratic, and then 0 at the other two nodes. And the same for the last one, is equal to 1 at the last node and 0 at the other two nodes. So you can still think, oh, okay, I'm going to associate this function with a node, but keep in mind that now we move away from that mindset, and now we're going to associate basically nodes to the region where the function is non-zero. Okay?
Yes.
Clear?
Yes.
Okay, so just to finish this, because it's already 42 minutes, let's just try to apply this to something that we are actually going to do in the project. So say we want to compute the stiffness matrix of our p-FEM implementation. And then this is again applied to the 1D bar element. So my ij component of my stiffness matrix is going to be EA d phi I dx d phi j dx. Notice the derivatives with respect to global coordinates, right? Now I'm going to change that, and I'm no longer going to do integration there, but I'm going to integrate between -1 and +1, my master or canonical element. And now, because my shake functions are defined in terms of those coordinates, I'm going to have to basically apply chain rule. And notice that, of course, the Jacobian of the interpolation shows up because I changed the domain of integration, which is basically this one is my L2 divided by 2. And these two terms is basically 1 over the Jacobian, which is 2 divided by LE. And so this whole integral is going to be 2 divided by LE, which is the length of the element. And now I transform that integral into a sum of integration points. So EA evaluated at my CI is my integration point, or my quadrature point, and then I have this d phi I also evaluated at that integration point. And then I have my gamma I, which is the weight that is associated. Notice that this and the product of these two is basically here. Okay, and so the same as before, if you remember, n Gauss points, integrate exactly a polynomial of order, what? Of degree 2n minus 1. Okay? And with this, we finish this lecture for the p-FEM in 1D. Do you have any questions up to this point? Clear? Okay, we stop here for a few minutes before we move on to p-FEM in higher dimensions, okay?